Action.
All right, so today we're going to talk about the life cycle of a star.
Yeah, a real star, not like the Kardashians, but something actually important.
Right.
So what's a star, guys?
Well, I learned from The Lion King that it's a ball of exploding gas.
Millions of miles away.
Millions of miles.
And actually, that's pretty
It's not bad.
pretty good.
Yep.
That's pretty close.
Yay!
They have enough gas to burn for billions of years.
Yes.
So a long time. And as we're going to go over, their appearance can range in color, depending on how hot they are, and also size, depending on how old they are, or how big they were originally. But they tend to get bigger through their lifetime, and then smaller.
Yeah, and we're going to talk about that in just a little bit. We'll talk about the color and size and all that stuff.
So how do they classify stars?
Based on their color and their size.
Okay.
Yeah.
Just making sure.
And we're going to get to that. So, but stars are made of hydrogen and helium mainly, okay? And really, hydrogen's the main one, and you get helium because the amount of energy in any star causes hydrogen to fuse together, two H atoms, and those one proton each. So 2 protons in the new atom, and that makes helium if you want to check your periodic table. And this releases heat and light energy, and that's the energy that any star
it's a
releases.
nuclear reaction that gives off heat and light.
Atoms being fused together into new atoms, releasing energy. That's how any sun gives off energy. And they could actually be converted into heavier elements. So we have here carbon, nitrogen, and oxygen, but in reality, you can do this even all the way up to, well, any atom.
Pretty much anything that's naturally made.
Any atom that is on this planet.
Just keep fusing and combining them, and every time it fuses and combines, you give off energy in the form of heat and light. That's what our sun's doing all the time. It's pretty awesome.
This is the main way in nature that you get any atom that is not hydrogen.
And all stars do this, not just our sun.
Mm-hmm.
So, Mr. Harkins, can you please tell me, how do we actually name a star?
We name a star based off of its color and the surface temperature. So you will see things where they'll take into account like the size, temperature, and color, and you'll get things like the red supergiant or different things like that, white dwarf, different things like this, which have to do with color and size. Cool. And the color changes with regards to like the temperature of the sun or the temperature of the star. So you're going to have like some of the hotter ones are going to be blue or white. You're going to see those around like 54,000 degrees Fahrenheit. And then yellow or orange, a little bit cooler, still ridiculously hot. It's about 10,000 degrees Fahrenheit. And then you're going to have the cooler, older, bigger stars that are red. They're burning cool as far as we're concerned.
Relatively speaking.
Yeah, and that's about 5,500, 5,400 degrees Fahrenheit. Now this is surface temperature, not at the heart of the star, not at the core of the star.
And what's neat is that follows the electromagnetic spectrum, too. If you think that blue has the highest energy, it's the highest temperature. Red's the lowest energy. It has the lowest temperature.
Man, we keep talking about energy and waves. It's almost as if
the entire universe
connected.
is founded off of all of this,
Ooh, good physics.
So speaking of that, let's talk about luminosity and brightness, Mr. Black.
So in addition to the whole color and temperature thing, we have the idea of luminosity and brightness, which are not exactly the same thing. Luminosity is literally the amount of light actually produced by the star, meaning if you were sitting right next to that star and were able to measure the light output, that's what your luminosity is. Okay. And it's caused by the nuclear fusion that's happening at the center of the star, which is at 15 million degrees Celsius.
So not the surface, what we just talked about. This is the heart where the reaction's really happening.
Indeed. So what you get is what's called the absolute magnitude for the star, which is literally how bright the star actually is. Now, the brightness is more of like an appearance factor. So how bright does the star look based on its luminosity and its distance from us? So now we're looking at not just like what it actually is in terms of how much light there is, but when you look at it, well, how does it appear? So and that's called the apparent magnitude because it appears to be a certain brightness.
So the luminosity is how bright it actually is, or actually how much energy is produced as light, actually.
Right.
The brightness is how much light it appears to us, and that's going to be affected by distance.
Exactly. Right.
So like a flashlight 2 miles away is not going to look as bright as a flashlight right up close, even though they may have the same luminosity. They will have different brightnesses.
Right.
Got it.
You got it.
Excellent.
So let's actually talk about how a star gets formed.
Speak some stars.
A star is
Star
born.
babies.
Yay!
Anyway, so as we referred to in our Big Bang PowerPoint or video, all stars begin as in nebulas. Nebulas are giant clouds of gas and dust particles, and what eventually happens is gravity draws a lot of that stuff inwards, into these circular-ish clouds called protostars. Proto usually means before.
First version or before,
first version.
or like a prototype.
An early
version.
star.
Yeah.
Right.
Yeah. So it means an early version of a star. Okay. Now what happens after that, as gravity starts to bring those particles in, and the protostar shrinks, and particles begin rotating a bit, and they collide with each other, and they rub with each other, and that creates friction, and friction usually creates heat. And if you have this happening fast enough, that creates light as well. Okay. So now you have this energy that's going in this protostar, and that heat actually then causes particles to start fusing together. Those hydrogen atoms to start fusing and making helium. Okay,
Fusion
so
reactions.
So that
the
starts to
energy
where
for
you're at.
motion
Yep.
gets converted into friction, which gets converted into heat, and that creates fusion.
Fusion.
So
Which is
lots of
nuclear.
energy conversions going on here,
Escalating, stepping up
And-
and up and up.
and that starts to release energy, and at that point you get a star. Okay.
Yay!
Now quickly to talk about our star, our sun.
I love our
sun.
sun.
Yeah.
Sol.
Our sun is very, very normal. It's pretty average. There's nothing that special about it besides the fact that we're around it.
Right.
But
Very true.
It
important to
it
me.
burns at a medium temperature. It's medium sized. It's in the middle of its life cycle. It's right down the middle of pretty much every
Yay!
category.
75%.
Perfect for us, being that it's in the distance that we are.
Yeah,
Yeah.
exactly. But it
Right.
happens to work out right for where this planet is at. So good
Right.
for us.
Now, what happens though? So we've talked about stars and where our sun is. Okay.
Mhm.
Now, what's going to happen to any star is it's going to expand. It's
Yep.
going to slowly die out. Okay. And what happens is they expand to either red giants or red supergiants. Okay.
Which are probably bigger than red giants.
Yeah.
Thus the name,
most
again, color and size.
yeah most
Cool.
most stars expand into red giants. Because not that many stars are really that big, but
Right.
the main stars, or the most common stars, expand to what's called red giants. They get bigger. You can see from that chart. The yellow is what our sun looks like now, and the red is what the red giant version of our sun is going to be in 5 billion
Gonna
years.
expand a
It
lot.
cools down though, and as we said, red is a cooler temperature.
So it's burning less hot.
And the
Right.
reason why it expands is because it's starting to run out of fuel, so
Right.
it doesn't burn as much. So all that
Right.
energy and stuff just allows it to drift
Yeah.
outwards.
Right. So then what happens too is energy as stuff gets further away from the center and less
Compressed.
pulled by gravity too. Some of that stuff sort of
It
fades
dissipates,
off,
it spreads out,
dissipates,
goes
and
away.
all that hydrogen, any of those atoms go off into the universe to
Right.
be taken in by another gravitational field.
Yep, maybe another nebula, maybe rain down on
Maybe
the
they'll become
planet.
people. Who knows?
Yeah.
But anyway, because that's where your atoms came from, with stars.
Because
You are all made of stars.
14 billion years old.
But anyways, the red giant pushes its outer layers into space. The rest of it collapses on itself and makes this small thing called a white dwarf. And they have a very large gravitational field because they're super dense, because everything condenses inwards. And they burn white. And they burn pretty hot. And that's...
And
Yeah.
that's all due
Yeah.
to just the energy of the force of the collision.
Right.
Right.
As
And,
we
the
causes that
remaining,
light.
and the remaining heat that's been trapped inside as it dissipates outward.
Right.
So.
Yep.
Now, if you have a red giant that collapses on itself, a red supergiant, excuse me,
Right.
that collapses on itself, we call this supernova, an explosion of a very large star.
Right.
It could create new nebulas, but also all that matter when it condenses makes such a heavy, dense area. It's called a black hole because it is so dense, it has such strong gravity that it sucks in light
So
itself.
even more dense
Light
than
can't
that
get
white
out.
dwarf.
Right. Light
It's the
gets
black
sucked into
hole.
it because it has such
Yeah.
strong gravity.
So photons are actually pulled into. That's amazing.
And what do we call the absence of color and the absence of light?
Black.
Black.
Yeah,
So,
so that's the black
it's not like colored black. It's black because all light gets taken into it, so no
There's-
light escapes it. So you can't
Right.
see anything where it is.
Nothing. Yeah.
Yeah, it looks like nothing, but there's
It's like an
mass
empty.
there.
It's like a hole or a blot that's just
Yeah,
missing.
it's a spot
Yeah.
where nothing is there, and we recognize it by what is not there, which is anything else, signs of
Right.
stars or planets or anything else.
Yep.
Right.
So,
Now on the flip side, you can
Well,
get
Another part, Mr. Harkins, maybe you could fill us in, is called these. What are these
the
neutron
stars are actually really cool. I like these things a lot. They're actually really neat. It's if you get a supernova, you could have a very dense neutron star formed out of that. And just to give you guys an idea, like a neutron star is like so ridiculously heavy that you have had a amount that fit in the palm of your hand. It would be like all of the planets in our solar system times probably 15 crushing your hand down in that little glob.
Mm-hmm.
Super duper dense, and that is not a scientific term, super duper. But one type of neutron star of this super dense astral body here is called a pulsar.
They're
And
pretty
it
cool.
gives off a rhythmic pulse of radiation. That's the pulsing, where,
Yep.
depending at different rates, but it is usually pretty steady, so much so that you can actually use it as a measurement of time or a unit to base time off of.
And they do.
And they will blast out, and it's kind of polar, and they will blast out pulses of radiation. It's very cool stuff, guys, and that's another thing that can happen when stars die.
So here's a little chart showing the general life of a star. So if it's an average sized star,
Like
starts
ours.
as a nebula, goes to
Yay.
average star, turns into a red giant. Eventually, a lot of that stuff is going to blow off into a planetary nebula, and the stuff in the middle becomes the white dwarf.
Yep.
Okay. Now, if it becomes a massive star, it'll become a red supergiant. It will supernova when it explodes. It'll become either a neutron star or a black hole. Now, what's that stage between nebula and?
But it isn't a
actual
real
star?
star yet.
Protostar.
Yeah, right.
It's a
So
protostar.
protostar goes there, right?
All stars come from nebulas, and they usually
But I'll
go
tell you
back.
what's not a star.
What's
a
not
shooting
a star? No,
Oh,
They're
they're
actually
not.
meteors.
What do they call it?
They call it that because they got its name before we realized that they're not really stars. It's kind of
Really
like when
just-
they started calling starfish when
Right.
they're not fish at all. But
Stupid,
maybe we'll leave
primitive
that conversation
humans.
for bio. But anyway, so these were named before we knew a lot about stars. That's
Yep.
why they're called shooting stars.
They look
They're
like
really
it.
just meteors or dust from a comet.
Right.
Yep.
Rocks
Friction's
and
causing
bits
them to
running through.
ignite and kind of burn as they come through our atmosphere.
Right.
Now,
Go ahead.
I was gonna say another thing we get. So we get all these individual stars and how they are made and how they die and stuff. And sometimes you get a lot of stars that stay relatively close to each other.
Right.
I say
'Cause they're all made
relative.
from the same nebula,
Right.
right?
And I
Yeah.
say relative because we're talking
Many stars
astronomical
form out of that
distances.
huge nebula cloud.
So you end up with these things called star clusters, which is basically just a large scale group of stars. And there's dust
Lot
there
of
too.
stars.
But they're just kind of held together by gravity. So they're not close enough where they collapse on each other, but they're close enough where they don't continue to move away
They all
from
kind
each
of
other.
pull on each other and kind of
Right.
keep each other in proximity
in
of
place.
each other. They won't actually spread out too much.
Yep. Two main types. You got the open star clusters, which are very, very bright young stars. They are widely spaced apart, relatively speaking.
Yeah.
And they've got about anywhere from 10 to 1,000 stars roughly. And you can see these with the naked eye, so you can see them. And basically, when you look them in the sky and you see a large number of stars that are closer to each other than some other stars, you're probably looking at an open star cluster. Now, a globular star cluster is usually older stars, which means they were made much longer. There's usually a lot more of them there, so tons and tons of them. You need a telescope to see these, but even with a telescope, you're basically just going to see kind of like a fuzzy blur.
Because there's so many, they're overlapping. So
Right.
It's
It's just a big overloading of the
thousands
telescope.
and thousands of flashlights all shining at you. Kind of look like one big flashlight because they're not spread out very far.
Right.
Of course, we're talking on a universal or at least galactic scale.
Yep. So
Here's what
there's
those all
Good
look like.
pictures.
Yep. The open cluster, you can see there's a lot more space between
Yep.
the stars.
Look
Globular.
at the different colors of them there too.
Yeah, pretty cool.
Yeah.
All
pretty
right.
neat.
And that will be it for now.
Do
so
checkpoint, guys.
do your
Almost
checkpoint.
Done.
see you later.